Great. Hi, everyone. Welcome to the Data Science for Health Equity Statistical Methods for Health Equity webinar series. This is a monthly webinar series focusing on statistical and machine learning methods that have the potential to advance health equity. So, for example, methods that shed light on the complex factors underlying inequalities or fairer algorithms that appropriately take into account the biases that exist in biomedical data sets. I should introduce myself. My name is Bria Lehman. I'm an associate professor in statistical science at UCL in the UK. I'm also one of the co-organizers of the statistical methods theme at Data Science for Health Equity. So this particular webinar series is co-hosted by the Alan Turing Institute and specifically the Health Equity Interest Group within the Alan Turing the UCL Statistical Science Department, where I'm based, and Data Science for Health Equity. Data Science for Health Equity is a global community of experts and enthusiasts working at the intersection of data science and health inequalities. And the aim of the community is to ensure that the latest research and innovations in data science, machine learning, and AI serve to improve everyone's health, and especially those in underserved populations. If this sounds like something you're interested in, there are a few ways to get involved, and we'll post them in the chat very, very shortly. So today it's my great pleasure to welcome Amanda Coston. Amanda is an assistant professor of statistics at UC Berkeley, having earned her PhD in machine learning and public policy at CMU, Carnegie Mellon University, and subsequently a postdoc at Microsoft Research on the machine learning and statistics team. Amanda's research addresses real-world data problems that challenge the validity, reliability, and equity of algorithmic decision support systems and data-driven policymaking. And so she's a really great speaker for this webinar series. So without further ado, I'll pass over to you, Amanda.
Yeah, thank you so much for the really nice introduction, and thanks for organizing such a great seminar. I love the intersection of topics that you're focusing on here today, and I'm really excited to share my research. So I'm going to be talking about some work today on developing methods to evaluate predictive models, predictive algorithms that are used for decision-making settings. And a lot of our motivation is going to come from healthcare medical settings. And in particular, we're focusing on the challenge where we have covariate shift. So where there's a difference in the distribution under which we trained and evaluated the algorithm initially versus the one that we're thinking, the population that we're really interested in deploying the algorithm on. So to make that a little bit concrete, I'll talk about an example of a clinical decision support tool from the MD Calc site called the Heart Score. And the Heart Score is a risk assessment for major cardiac events. And as you can see here with this screenshot, it has doctors can access this tool via the MD Calc site where they go through these questions and they will assess the patient's history, saying whether it's slightly suspicious, moderately suspicious, provide input about EKG, age, risk factors, and at the bottom, after answering these questions, they'll get a score. So here for the answers I've put in, the score is 6 points, and it says that this is a moderate score because it's falling into this range of 4 to 6 points, where they're recommending admission to the hospital for further clinical observation and further like workup and testing. So this is an example of a clinical decision support tool that's informing decisions about, whether the patient can be discharged, should be admitted for further observation, whether they should undergo further testing. And one of the concerns where this covariate shift piece comes in is that this is widely used here in the U.S. I think in other countries as well. Although I'm not as sure about that, but it was actually developed. The tool was developed in the Netherlands. And the cohort that they developed the tool on and evaluated on initially, they didn't include race explicitly, so we don't actually know what the racial demographics was there, but they reported in this paper in the Netherlands Heart Journal. I have the citation at the bottom here, that the geographical area where the patients were drawn from, where they were living, was about over 95% white or Caucasian. And so, that's a very heavy skew toward white or Caucasian demographics, and that's particularly noteworthy for doctors who are working in, settings that might have a much more racially diverse population, and they wonder, is this still the right tool to use for their patient population? Like, are the performance properties that we saw when, this was initially evaluated, and the evidence you can see on this, I guess the tab isn't clear here, but on the MD Calc site, there's like an evidence tab, and you can click on that, and it gives some of the performance metrics that they use to validate this. But the question is, do those performance metrics hold when we're looking at a very different population? And I forgot to mention at the start of the talk, please feel free to jump in with questions throughout. I don't mind interruptions. It might be hard for me to see raised hands, so you could always just unmute yourself. That's totally fine. Um, okay, so this is some of the motivation for the kinds of problems we're going to be looking at. Um, and I think people in this group probably are well aware that there's been a lot of concern, a lot of media interest, a lot of scholarly investigation into some of the ways in which these clinical decision-making tools might exacerbate existing health inequities or cause new ones, and how we can kind of think about trying to anticipate these issues in advance and catch them in algorithms that are used in the real world. So that's all kind of motivation for some of the work we're going to present here today. Um, I'm focusing in particular on evaluation, and I'm making the claim that evaluating these decision-making algorithms that are used to inform decisions, is fundamentally much harder than standard prediction. So, if we think about the abstract, like machine learning setting where we're doing prediction, generally we feel like we have a pretty good idea of how to do like evaluation best practices. You kind of have some, trained test set. You make sure your test set is a random sample, randomly spit from the training data, and then you can, evaluate on that and make sure you're not overfitting, and that, that's pretty straightforward. But things get harder when we're in this decision-making setting. And so I'd like to walk through that. We're still going to stay in the clinical setting, but in a slightly different. We're going to move from heart disease, which we'll return back through. But for right now, I want to talk about predicting pneumonia risk. And that's because this is kind of a well-known example from a paper back in 2015 by Rich Caruana and others. And I think it really illustrates the point that I wanted to make clearly. So I'm going to switch to this pneumonia setting briefly here. So suppose that we have some tabular data set and somebody wants to predict pneumonia risk. So we might have these covariates X1 through X4 as I show here, and then some outcome Y. Right. And so why are we trying to build this predictive algorithm? Suppose we want to use this to inform admittance to the ICU. Okay, so we have this Y that we might say that that's whether the patient actually developed pneumonia, and we have these risk factors, and we also can measure whether patients historically were admitted to the ICU. Now, suppose we look at this patient in row two, where this patient has asthma. That's what I've labeled as X2 here. So one here just denotes that they have asthma, which we know is a risk condition for pneumonia. But actually, this patient didn't develop pneumonia. And if we look at their ICU decision, we can see probably why. So they were admitted to the ICU where they likely got very intensive care, and they were able to mitigate that risk of pneumonia, and the patient had a good outcome. They didn't get pneumonia. The challenge is that if we don't consider that decision column, the ICU, when we build a predictive model, if we just regress Y, those observed outcomes on our predictive factors, and the reason we wouldn't typically wouldn't have D as a predictive factor, because that's something you're making after the algorithm spits out the decision. So even though we have it in this data, when we're thinking about building a new algorithm, we want to be able to input that for a prediction. So a simple approach would be just to build a model to predict Y based on X1, X2, X3, X4. But the problem is that that kind of approach is going to that kind of approach is actually going to screen out patients like this. So if we did that, it would say, it would think that this patient was low risk, and it would actually learn this unexpected and problematic association between asthma and pneumonia. And that's what they report in this 2015 paper, that that kind of approach of machine learning actually built a model that said that if you have asthma, you are at lower risk of developing pneumonia. And we just know that that's clinically wrong. Like people who have asthma are at higher risk. And what's going on is that they weren't teasing out the effects that people who had asthma were more likely to get admitted to the ICU to have intensive care. And that was why they had good outcomes. But counterfactually, if we changed their treatment, if we didn't admit them to the ICU, didn't give them those that good intensive care, they probably would have different outcomes, right? And so here I've modified the goal to say more precisely what we want to do in this setting is predict pneumonia risk if they weren't admitted to the ICU. And that's what's clinically relevant for the doctors making decisions. They want to know what's going to happen under a particular decision. So they want to know if I take the less invasive option or the less intensive treatment, we don't admit them to the ICU, is there still a high risk of these adverse outcomes? And so one way to think about addressing this is using, and this is kind of my own formulation in that original paper, they take more of an interpretability approach to addressing this problem. But I think that this is a really nice candidate for formulating things in terms of potential outcomes. And so I'll go through now a little bit the idea of potential outcomes and why that can be really helpful in these decision-making settings. So instead of thinking about just one outcome that we would always see, because we're in this world where we're thinking about how decisions affect outcome, that if somebody is in the ICU, they might have one outcome, they might have a positive outcome and not have any pneumonia. But if they don't go to the ICU, it's possible we could see a different outcome, that they actually would have pneumonia. So the idea is that we want to have notation to refer to those different outcomes, those different hypothetical or potential outcomes that we might see under different decisions. And so that's what I've added these columns on the right here. So we're using these parentheses notation to denote the decision. So we're asking in the rightmost column, what is the outcome we would see if we admitted to the ICU? So if D equals 1. And then in the column a little bit to the left of that, before the observed Y, we're asking what would happen if we did not admit to the ICU. And for some patients, maybe they would be low risk regardless, but for other patients, they might be high risk if we didn't admit to the ICU, and low risk if we did. And so these potential outcomes allow us to kind of talk about what would happen under those different scenarios. The challenge is right. So the target in this setting that we want to predict pneumonia risk if not admitted is this column, Y of 0. So that's what's clinically relevant, and what would be ideally, we would want to regress that on those predictive features to build our machine learning algorithm. The challenge is that we only observe the this column, the Y. So we only observe outcomes under the historical decision-making decision policy. So then the challenge becomes, how can we equate this observed outcome or use this to identify this hypothetical outcome that we really want to be our target of prediction? And we'll get into that a little bit later in the talk, some of the approaches for that. But really, like, what the picture to have in mind here is that we actually don't observe that column, right? So I put those numbers out just for the sake of talking about this. But what do we observe in practice? We only partially observe this Y of 0 column, where we can observe outcomes when D equals 0. So the patient in the first row was not admitted to the ICU, and the patient in the last row weren't. So that's why here I have that we can observe their outcomes, but we have a missing data problem for people who were admitted to the ICU. We don't know what would have happened counterfactually had they not been admitted to the ICU. Maybe they would have had the same outcomes that we observed, or maybe the outcomes would have been different. Okay, so one way to talk about this problem that I've proposed using potential outcomes to propose is selective labels, that we can say that we are only selectively observing those labels for people who historically got the decision that we're interested in predicting outcomes under. Another term that you see people use is calling this decision dependencies, so that the outcome has these decision dependencies. right? But the problem is, regardless of which kind of language you want to use to talk about this, the problem is that we're only selectively observing this outcome of interest, that potential outcome under the proposed decision we want to predict. We're only observing that under historical decisions, so we're only selectively observing that for a biased sample of the population. And oh, I'm just mentioning there's a paper here where we kind of talk more about the conceptual, this conceptual landscape and some of the challenges with addressing this, particularly when we're looking at human decision-making systems. So you could check out that paper if you're kind of interested in that. And okay, then now I will, with this kind of tabular exposition, I'll just bring in this idea of covariate shift. So we've already talked about how we have partial missingness in the target outcome due to the fact that this selective labels problem, that we don't observe the outcome of the interest for everyone in our data set. And then on top of that, if we're in this covariate shift setting, where we're thinking about using this tool in a population different from the one where the tool was originally developed, we have additional sources of missingness. So in this covariate shift setting, we're going to say that we have covariates for our target population, but we don't know anything about outcomes. And so you could think about this being like potentially like there's a new kind of hospital that's just been built, maybe say in like a rural setting. And so they're seeing the patient, they have a patient showing up and they want to make decisions on whether to admit them to the ICU based on a pneumonia risk. But we don't have this kind of outcome data or historical decision-making data because this is a news context. So the problem we're going to tackle today, we have both this partial missingness in the outcome column for everyone, and then additional missingness in the data that we're actually data from the population that we really want to focus on evaluating on. Does that, I'll just kind of give a brief pause there in case there are any questions on this setup. And I'll formulate it mathematically in a little bit too, if that makes things more concrete. But this is just kind of some motivation and conceptual foundations. Okay. So just to recap, we talked about selective labels, and then I introduced this problem of covariate shift, which is a type of distribution shift. And we can also see that as part of selection bias in the sense that we are observing the population where we actually have labeled outcomes is a different population from our target population, and we can approximate that as saying it's a biased sample of the target population. So we can think about this covariate shift problem, which is a type of distribution shift, as being related to selection bias. Okay. So now I'll just take a minute to discuss these issues in the context of our opening heart score clinical decision support tool. And then we'll get into some of the more formalization here. Okay, so the schematic we can have in mind is that a patient comes in and the doctor, fills out those answers to get a heart score on them. And then they might make a decision whether to admit the patient or to the hospital or to screen them out. Um, and if they admit them to the hospital, then they'll be under more intensive clinical observation, get supportive care, and we might observe a positive outcome. But suppose that same patient, they might screen them out, and if that patient was actually at high risk and should have been admitted, they could have a negative cardiovascular event. So that's this problem of decision dependencies and where we only selectively observe outcomes depending on the historical decision. Uh, and then where does this covariate shift piece come in? Okay, so on the MD Calc page, they give and in the original paper, this Six Backus and Kilder paper, they give this guidance for how to use scores. So they say that if you have scores 0 to 3, that means they have a 2.5 risk of any cardiovascular adverse endpoint, and they recommend discharge. If the scores are between 4 and 6, the risk is about 20% of any cardiovascular adverse outcomes. So they recommend admission for clinical observation. And if it's more than 7, it's 72%. right? But as we saw earlier, these numbers were calculated on a population that was overwhelmingly white. And so the concern is for doctors working in maybe a setting where their population is predominantly Hispanic or Black or a combination, they might wonder, like, are these numbers going to be the same, or should they adjust the risk scores? Like maybe they should make decisions. Maybe, the first bucket should be 0 to 4 or 0 to 2. So it's a concern about whether, these kind of calibration numbers hold for a different patient population. Okay, so the agenda for today's talk, we've already kind of done number one, introduced this problem of decision dependencies and selective labels, and also of covariate shift. And then next, we're going to get into how to do valid evaluations when we have these kind of problems, and think about kind of some of the conceptual ideas around what does it mean to be a valid evaluation. And then we'll get into the actual statistical techniques to addressing these problems using techniques that are widely used in causal inference and really helpful for these missing data problems. Okay. So, by valid evaluation, we mean that the evaluation should be assessing the intended quantity. Or more informally, like, does the evaluation assess what it's supposed to? And this idea of valid decision-making algorithms and valid evaluations is something we explore in depth in this SAT-ML paper from a few years ago. So I'll just go over some of the kind of ideas from that paper that really connect to the work I'm presenting today, but we consider a broader array of things. So if this is interesting to you, you might want to check out that paper afterwards. Um, but validity, has a long literature in other disciplines, in social sciences, in experimental design. And so we can connect those core validity concepts to some of the challenges we've been talking about here today to understand why failure to address these challenges can threaten the validity of our evaluations. So the first core validity concept we can start with is construct validity. And so in social science, this measures the extent to which the measure captures the intended concept. So this assesses the extent to which the measure captures the intended concept. And then if we map this to our decision-making setting, that's asking to what extent the evaluation assesses the intended quantity. And the other core validity concepts that's relevant to the challenges we've been talking about is external validity. So external validity typically asks to what extent claims hold true in real world settings. So when you're thinking about a study that was done in controlled settings, you want to know, like, to what extent are those externally valid for the real world. And then if we map that to our decision-making setting, we're asking to what extent metrics reflect how well the algorithm will perform in the real world settings. Okay, so can we map those to the problems we've been talking about today? The first set of issues, the selective labels problems, this threatens construct validity because observed outcomes are not valid to evaluate against when we have these decision dependencies that are causing intervention effects, right? We saw for that patient who had asthma and was admitted to the ICU, that's not really the right outcome to evaluate an algorithm against. We would want an algorithm to be flagging that patient as high risk, even though their observed outcome was low risk. Right. So if we were to use those observed outcomes, that could threaten construct validity. And we show in some work that, if you ignore this and go ahead with that, you can get kind of really poor outcomes. Like you might choose a less performant model if you're trying to do this evaluation for model selection, or a less equitable model, or perhaps you have, a bar for threshold of performance that below which you're not going to release a model. And this could lead you to kind of green light models that you really wouldn't want to be releasing if you had an accurate picture of their performance. And we can also connect this to the idea of external validity, because when people realize that these observed outcomes are a problem, oftentimes the kind of first step of remediation is to just focus on the sample where we do observe the target potential outcomes. So this is really common, for instance, in consumer lending, where you're building an algorithm to predict whether somebody would repay a loan or not. And you only see whether somebody repays a loan if they actually got a loan. So what's common in that literature is you just kind of ignore all the unlabeled data and you're just going to look at what you're just going to, build an algorithm and evaluate it on the sample for which you observe outcomes. But when we do this, although, at least we were thinking about these decision dependencies. The problem is that bias sample is not representative of our target population. And so that's a threat to external validity. And again, we can risk choosing a less performant or a less equitable model if we do that. Okay, so then the second set of issues, distribution shift and selection bias, also connect to these validity issues. This is also a problem of external validity because the data set is not representative of the target population. Again, if we fail to address this, then we may choose a less performant or less equitable model than what we would if we were really addressing these issues properly. Or we can even risk greenlighting an inequitable model because it may look like when we evaluate performance properties on this selectively biased sample, it may look like the model is pretty equitable, but if we really were to consider it on our target population, we would see that there was an inadmissible level of inequity. Um, so we've talked about this challenge that is in this paper. Uh, they discuss this challenge of clinical decision instruments being developed for more examples than just the heart score that we talked about. A number of clinical decision instruments are developed using samples that are really not representative of a lot of the patient populations. So if you're interested in kind of understanding that context more, I'd encourage you to check out that paper. Okay, so now we can get to how we can actually address these validity issues. And this is joint work with my PhD student, Annie Ulichny. And we can situate this in prior work. So what's been done previously to address these issues? People have been thinking about selective labels and decision dependencies and covariate shift for a long time. On the selective labels and decision dependencies, there's often imputation work that's trying to kind of estimate those missing counterfactual outcomes. And we can even use double machine learning or doubly robust estimation to do that. So we will actually incorporate those techniques in our work later. So I'll talk a little bit more about what that means. If you aren't familiar with that term for now, just ignore that. For covariate shift, this type of distribution shift, there's often like importance weighting methods that will kind of reweigh your source population to make it look like the population that you really care about. And you can again bring in doubly robust estimation techniques there to improve that. But what's missing from the literature is something that can simultaneously address these issues. So right now, if you wanted to do an evaluation, you would kind of have to pick which issue you were more concerned about, and then there would be a method to address that. But we argue that in practice, these selective labels problem and the covariate shift can arise together, and we want a method that can address both of them. So that's the goal of our work here today. So we're going to propose a method to jointly address distribution shift and decision dependencies. Okay, so now I'll introduce some more mathematical notation so that we can talk about our evaluation approach and the estimators we propose. So we have this potential outcome. So this is the outcome we would observe under some hypothetical decision. So we're writing that y of 0 because we're assuming, like in a clinical context, often we want to know what would happen if we didn't do the invasive treatment or if we didn't admit to the ICU, if we took the less intensive option. And that's only partially observed. We can equate potential outcomes to the observed outcomes as follows. This is making a consistency assumption that I won't talk about too much now, but if there are questions on it, I can talk about that. But essentially, we're saying that the observed outcome for patients that got D equals 1, we're seeing that outcome y of 1. And for patients that get D equals 0, we're seeing that outcome y of 0. So this is how we can equate the observed outcome to potential outcomes. We're assuming that there's a binary decision or intervention. So you can think about this as admitting to the ICU or not, or in the heart score setting, admitting to the hospital or not. We have some predictive features that we can use that we're using to make those predictions in the clinical decision support tool, and also those are available at evaluation time. And then we have a population indicator to differentiate the population, the source population, which is the one that we originally had available to build the clinical decision support tool, the algorithm. And then so the R equals 1 will denote that source, and R equals 0 will denote a population of interest, the one where we really want to evaluate properties on to get a sense of whether it would work in our setting of interest. And then we'll use F hat to denote the model predictions. So that's the model we'd like to assess. And then we can write down the sample we observe as a tuple. So that's X, the covariates, R, the population indicator. And then we observe the decision when R equals 1. So that's the product RD. And we observe the observed outcome when R equals 1 as well. So that's also a product RY. And our goal is we want to evaluate, oh, I'm sorry, I changed the hat notation. Okay, so think about y hat as just being equivalent to f hat of x. And I'll try to call out any inconsistencies here in what I'm talking about. So, but we want to evaluate these model predictions. We can call those y hat, or if we want to emphasize that it's a function of x, f hat of x. And we want to evaluate that against y of 0 for samples in the target distribution. Okay. Okay, so then our next step is to write down the estimand. So that's the goal, that's what we want to evaluate, but mathematically, what is it that we'd like to assess? So here we're providing this distribution-aware estimand under selective labels. So here we're going to write down this loss function. So L is denoting a loss function of the predictive model f of x evaluated against y of 0. And we're going to evaluate this on the target population. So we're taking the expectation over the target population. Right, so this is the expected loss. We're asking about what's the risk on the target population. And this estimand, as I've written it now, is a hypothetical quantity that needs additional assumptions so that we can actually equate this to things we can observe in the data, or in other words, so that we can identify it in the data. And we need a couple sets of assumptions to do this identification. So the first set are standard causal assumptions that we'll make. And if you're concerned about these holding, which I'd be happy to talk about, there are ways to relax them. It makes things more complicated, but I've done that in some other settings, and that's actually one of the directions we're hoping to take this work in. So I'd definitely be happy to talk about that. But for now, to see this kind of first step in addressing this problem, we're going to make this rather strong assumption of ignorability, which is saying that the decisions are independent of the potential outcomes conditioned on our measured covariates and the source population. And so this is saying that, we've measured all the factors that jointly affect the decision and the potential outcomes so that we have no unmeasured confounding. Or in other words, conditioned on our covariates, this is as good as a randomized trial where we have randomized the decisions. The next assumption we make is positivity, and this is saying that there's no that the decisions aren't deterministic, that there's this kind of randomness in the decisions, so that every covariate strata has some probability of getting both treatment D equals 1 and treatment D equals 0. And then we already talked about this consistency assumption, which is really this is assuming that there are no interference between units. So it's not the case, like this would be violated in a vaccine setting where my risk of developing the disease might depend on whether people around me got the vaccine or not. Here we're saying that, the outcome I observe, it really just only depends on the decision I got. So those are the first set of assumptions that we'll need, but we'll also need some covariate shift assumptions. And the covariate shift assumption that we're going to make to make progress here says that the conditional distribution, the conditional risk of y. So here I'm using D just to denote, be more generic about y of 0, but we can still think about this as being like our target estimate y of 0. So the probability of having of for instance, developing pneumonia if you weren't admitted to the ICU, that is conditional on X, that's the same in the source and target populations. So so when we're thinking about there being this distribution shift between the two populations, that's only happening in the marginal distribution of X, not in the conditional distributions. And then we also will make this bounded likelihood ratio that we can think about as saying that there's like this sufficient overlap between the two populations, the source and target populations, that if they were too different, we couldn't actually make progress with our problem here. Okay, so under these assumptions, then we can identify our target risk estimate, and I'll go through that now, what that looks like. So under the assumptions we just talked about, we can write our target estimate as two quantities. So in this first quantity, we're writing it in the expectation with respect to the target distribution. We can write it as this uh, expectation over this nuisance function mu of x, which is the expectation in the loss conditional on x r equals 1 and d equals 1. So if you're kind of familiar with causal inference literature, you might be familiar with this kind of in the more standard like average treatment effect setting, you would have mu of x is like the probability of getting y equals 1 conditional on x and d equals 1. So this is kind of the analogous version for our problem where we're looking at evaluating the loss. But we're also going to provide another identification because, as we talked about, it's challenging to actually do the estimation on the target population where we don't observe outcomes. So we want to also identify this quantity as something where we're taking the expectation over the source population. So that's what we're showing on the right-hand side here. The expectation that's subscript S denotes the source population. And here we have this likelihood ratio of the densities in the target over the source. And then we also have an inverse weighted a propensity score. So we're looking at D over pi, which is the propensity, the probability of getting treatment. Um, and then we're using that to reweigh the loss function in the source population. And that so once we do those reweighings, we could compute the loss in the source function adjusted by those weights to identify our estimand. Okay, so all of this means that we have written a way to equate our hypothetical target quantity in terms of things that we can estimate in the data. And so now all that remains is for us to write down how we're actually going to do that estimation. And I gave a little preview before that we're going to use these double machine learning techniques or doubly robust techniques that have been used in a variety of other settings, including when people were addressing these problems in isolation. And at a high level, the doubly robust approaches, they are uh, they are operating where we're estimating both these nuisance functions pi of x, which is the propensity score model, and mu of x, which is this regression function. And so we're going to estimate both of those and use that to get a better estimate than other alternative approaches that might just be able to estimate one of those. So at a high level, just going back to this, you could sorry, let me because we have this first identification that's just estimating that's just writing our estimand in terms of the expectation of mu of x over the target population. You could imagine if we built a model of mu of x, maybe you would just average that over the target population and you could get an estimate of your target quantity. So that could be one option, but that's not one that we would say uses this double machine learning procedure because that would only be using mu of x. And we can actually do better if we're building both a model of mu of x and the treatment propensity score pi of x. And so I'll read through our estimator here and then kind of discuss how we develop this and why it's useful. So if we look inside this the summation, we have and we look actually, let's start on the rightmost side where we have that mu hat of x. So we're taking that estimate of our regression model mu hat of x. So this is an estimate of the conditional loss given x. And we're going to add that into our estimator for people from the target population. So when R equals 0. And then this first term inside the summation is a bias correction piece. So for samples from the source population where R equals 1 and where the D is the decision of interest, we can actually do a bias correction because we can compare the observed loss against our estimate of the loss. And that bias correction piece is what makes this estimator have nice theoretical properties. So altogether, those two pieces create our pseudo outcome, and then we're going to average that over our population. And we're just also going to scale that by this 1 over rho term so that we're getting the right estimand. And where, because rho is just the probability uh, of being from the target distribution. And so okay, so we have this bias correction piece that if you're in the reason they call these doubly robust is that if you're using parametric techniques to estimate mu and pi, this would say that you're robust to misspecification in one of those, so you would only need to get one of those models correct. In our work, we typically work in a more non-parametric or flexible setting where we're using like random forests or other flexible machine learning techniques to try to learn those models as flexibly as possible. And there, the advantage is one of rates. So we can get faster rates when we're using these double machine learning estimators than if we were just using something that only depended on mu of x or y of x. And the reason is because we constructed this particular format and this bias correction comes from the efficient influence function. So the efficient influence function for an estimand can is a mean-centered quantity that shows us how to construct estimators that have these nice theoretical properties that can be these doubly robust or double machine learning style estimators. Okay, so that is the estimation approach we propose. And now I'll kind of illustrate this in practice on some data from the EICU data set. So still in this context of thinking about admission to the ICU. In this data set, it consists of patient admissions across various hospitals in the ICU. So we're going to use that to define our covariate shift. The data includes gender, ethnicity, age, vitals, an ID for the hospital. And we, for the experiments I'm going to show here today, we're going to do a semi-synthetic approach so that we can actually evaluate against ground truth. So we're going to use these real-world covariates to capture real-world covariate shifts. But then we're going to generate the potential outcomes and the treatment decisions so that we can compare against ground truth. And so I put down the specifications here, how we generate those models, and then, sorry, how we generate those variables. And then we will train a predictive model on a fixed source hospital to emulate the setting where, somebody trains a model on, one particular geography, one particular hospital. And then we're going to evaluate that on hospitals with different demographics. Again, emulating the setting where you train on one particular context and then it's more widely deployed. So like that heart score was trained in a particular setting in the Netherlands, but now it's deployed across the United States. Okay, so here are some results. And just to orient us, the panel on the right is the source hospital. And this was one that was chosen to be kind of roughly representative of the average kind of hospital in the population data set, in the EICU data set. And then here on the left-hand side, target hospital 443 is one that has a patient population that tends to be younger and consists of more Black patients than the source population. And so we have this legend at the bottom that's telling what each of these curves are. So we're plotting on the y-axis an estimate of the risk, the expected loss of the predictive model. Against on the x-axis, we're varying the selection strength in that data generating process where we're synthetically generating the decisions and the outcomes. So we can compute the true risk because we're in the semi-synthetic setting. That's the advantage of doing that. And that's shown here in red. And then our method is blue. That's the double machine learning, is what we're referring to DML. And then we compare this against approaches that are addressing the existing approaches that are only addressing one of these issues in isolation. So CS only refers to the approach that's just addressing covariate shifts. So it's reweighing to address the covariate shift between the target and source distribution, but it's not addressing those selective labels decision dependencies problem. And then in purple, we have a method that is addressing those selective labels problems, but is not addressing the covariate shift. And so what we can see if we start on this right panel, the source population, that the R method performs almost exactly the same as the selective labels one in the setting where we don't have covariate shift. So that's kind of what we would expect. And the covariate shift method performs, it's underestimating risk a little bit with respect to those, but the confidence intervals, whether that's actually statistically significant is unclear. And then if we consider on this setting on target hospital 443, where we actually do have covariate shift, we see that the selective labels model, that purple curve, severely underestimates risk. It's definitely significant there. And that our method is closest to the true risk. Although, yeah, depending on the selection length strength, the covariate shift method seems to perform somewhat comparably to our method. So the conclusion here is that failure to address covariate shift can mistakenly deploy a poor model, right? So if we think about someone making a decision for hospital 443, if they were just using that selective labels model, weren't thinking about covariate shift, they might they might think that this risk is low enough, around zero point 0.3, for something that they would want to deploy. But in reality, the risk is higher and might be higher than the allowable threshold. Would suggest that they need to go back and work on improving the model for this particular patient population. Um, okay, so I will recap a little bit, and then I'd love if there's time to take any questions or kind of open this up for discussion. So we chatted here about the challenge of does the evaluation assess what it's supposed to, and why in practice in these decision-making settings that's really hard because we have decision dependencies that cause the selective labels problem, and we also have distribution shift that we might care about a target population that's different from the original source population. We proposed an evaluation methodology that uses doubly robust estimation to jointly address these problems, and saw in practice on this semi-synthetic experiments how that can make a difference. And I will just mention that, yeah, most of the work I presented here was in collaboration with Annie, but I also mentioned some other papers with some of these other fantastic collaborators. And I would love to thank you all for your attention.
Thank you so much, Amanda, for a wonderful talk. And I should also doubly thank you because I know it's really early over there in San Francisco. So thanks for doing this so early on in the day. I'm going to stop recording so people can just ask whatever questions they wish.